Hi class, Dr. Searcy here with the video lecture for the Chapter 7 textbook lecture notes. To begin with, the title of this chapter is Probability and Samples, the distribution of sample means. One thing I guess that you can get from this title is we're taking everything that we learned in Chapter 6 about probability and samples, and we're now going to use that in a new type of distribution called the distribution of sample means. Maybe what you can do at this moment is just kind of get a sense of what do you think it's meant by this term. First, we can remember that a distribution is like a table or a graph. Lately, the way that we've been talking about distributions is in terms of not just a graph, but a curve that represents a graph, right? And from here, I want to begin explaining the Chapter 7 material by first doing a review of what we were talking about in Chapter 6. Basically, what was the important stuff that you need to remember as we move forward into this new Chapter 7, where we're going to be talking about this new type of curve, the distribution of sample means. Okay, so first thing that you want to remember that you learned in Chapter 6 was how to handle a situation like this, right? So you're given some kind of mathematical expression / equation. By now, you want to understand what this part of the statement is saying in particular, right? So you want to understand that it's asking what the probability is that you're going to reach into some distribution and you're going to pull out some x, and that x is going to be less than 120. Okay, so that's the first thing that you want to understand at this point in the class. From there, I guess the other thing you want to understand is how you will answer that statement. How will you get the answer to that question? Here, in this example, the book is offering you like the steps that you take. The first thing that you do is you take that statement of less than the 120 and you turn it into, from some x value into some z value, right? So you do that transformation that we were talking about beginning in Chapter 6 with the z-score formula. What you want to see at this point is that that's exactly what we did. We took the 120, we turned it into the z of 1.33. Why did we do that? So then we could take that 1.33 and look it up at our unit normal table, that UNT, to get the sense of proportion or probability with regard to what this statement is saying. Okay, so let's also think of how this works in terms of the graph that it may express. Right, so again, we're saying this is a distribution. In this case, it's a distribution of x values where the mean is 100. Looks like we're talking about a population distribution since we're using Greek letters or Greek symbols to represent our stuff. But we've got this mean of 100, standard deviation of 15. And so one thing that you want to get from that is where is this value 120 that they're talking about with regard to that standard deviation, right? So if a standard deviation is 15, then that's saying that that's how far one standard deviation unit is from the mean, 15 ticks away. From here, now I'm hoping that you're really starting to see what this statement is saying now with regard to the curve, right? So it's saying, what's the probability that I'm going to pull out this x of 120, but just not the x of 120. I want to know what's the probability that I'm going to pull out an x that's less than the 120. So an x that's anywhere in this region, right? That's what they mean by the less than 120. Okay, so as I was saying, you take that x value and you transform it into a z value. I've done that here. Right, and you remember that the z formula is basically z equals some x value minus the mean of the group that it came from over the standard deviation, right? So that's exactly what we have here. This x value is the 120 that we're talking about. The mean that I have is that mean of 100, and that standard deviation of 15 is the standard deviation that they're talking about right there. So that's how, so we conducted the calculation, and that's how we get this 1.33. From there, remember what you're supposed to do now is look that 1.33 up at the unit normal table and use that to figure out what is the proportion that we're talking about in this question. In this case, when they're saying that we're looking for this x that's less than 120, as far as the columns in the unit normal table are considered, right, there's that the tail, the body, and that D section. Here, it looks like the column that we're going to be talking about is the body column. Why the body? Because they're talking about most of this area under the curve. So when they do that, that's when they then find this value of this 0.9082, right? So if you were to go to your textbook, go to the unit normal table in the textbook, look up that value, that z value of 1.33, you'd see that in the body column, there's that 0.9082. So what is that saying? That's saying that there's this 90.82 chance that you're going to pull out some x that's less than the 120, right? And we're saying that because that's how much of the curve is contained in that area that we're referring to. Okay, so that's one bit of review that you really want to understand as we're moving forward. Another item that you might want to remember that comes out of chapter 6 is what they're talking about with regard to this curve, right? So first, they're talking about basically the same kind of idea. They have a curve, and they want to know what percent of the curve is this area of interest. The way that they're referring to it is as this middle 90%, right? So how much of the curve is in that middle 90%? Here, you basically do the same thing that you did over here to find out that proportion, but you just have to use a bit of a different technique. So in this case, we are given our x values of interest. What we need to do is transform each of those x values into a z value, right? Because then what we can do, once we have a z value, we can then look at our unit normal table D column. Remember, D is where they're telling you what's the distance from some x value of interest to the mean. Okay, so how am I going to do that? In this example, all I did was I picked one of the two x values, and I said, okay, I'm going to turn that into a z value. I ended up picking this 7.28. What I found was that, so 7.8 was the z value of interest. I subtracted it from the mean, or the mean from it. There's the mean there, and then divided that by the standard deviation. That gave me this negative 1.65. Okay, so now what I'm doing is I'm going to the unit normal table to look up this 1.65, and I'm going to go to the D column because I want to know what is the distance from that point to the mean. Okay, and what I find is that it ends up being, I'll go ahead and we'll look it up. I thought I wrote it down. It looks like I didn't. Okay, so I'm going to go to the unit normal table. I'm going to find 1.65 because it doesn't matter if the number is negative or positive. From there, I'm going to go to the D column, the proportion between the mean and the z, and I see that I've got a 0.4505. Right, so 0.4505. What does that mean? That means that from here to here is 0.4505 of the curve. If that's the case for that distance, it's also the case for that distance, right? And so now what we see is, what does that 0.45 add up to? It adds up to that 90%. Okay, so that's the review that you want to see from chapter 6. Basically, what we're talking about here is how to solve the problems that were featured in chapter 6. And we're going to use that information, that we're going to continue to use that understanding to now answer questions in chapter 7. To begin with, though, I need to explain a couple of new terms. And one new term is this thing called sampling error. What is sampling error? Well, it could be written as a formula where we say that sampling error is simply a population mean minus its sample mean. Right in here, I've got a blank to express the idea that we might have some number that exists here, right? Some number that's the difference between your population mean and your sample mean. Just to make sure you understand what we're talking about with this, let's go back to the idea of talking about it in terms of distributions, right? So at the beginning of the semester, we said that a researcher is interested in making a statement about a group such as this, right? Some population. How do I know this is a population? Because under the curve, we've got our mu. So the researcher wants to be able to say that this population looks a certain way, maybe in terms of its histogram, right? By the way, I've got these x values here representing the different places in the histogram, right? And the x values are just saying that's who is inside of each bar. You have some participants answer here, some participants answer there, and some participants answer there. It's on that particular part of the number line, and the bar is going to be so high because here it's saying it's 3 participants high. Okay, so we want to make some kind of statement about this population. But the only way that we can make that statement is if we get some score from everybody in that population. Remember what we said, going back to chapter 1, though, is that we can't always get to everybody in the population. And so since we can't get to everyone in the population, we are going to pull participants out. And we'll just say that they're just X's at this point. I'm just going to a participant, asking them a question, and they're giving me some answer, right? So this is an individual participant's answer here, another participant's answer here, and here. What am I doing with these answers? I'm throwing them over into another distribution that I'm now going to call my sample distribution, right? So everyone came over from the population. Once they came over, they created a new distribution, and now this new distribution represents just the people in my sample. So now this is where we're talking about this idea of the sampling error. The mean that you get with your sample is not going to be the same mean that you had with your population, right? There isn't everyone here as there was over here, and so they're going to give you just a different mean overall. We, the researchers, are interested in what's the difference between the population's mean and its sample mean. And that we refer to as the sampling error. Error is basically meaning like how is this group different from that group, right? And that's what we mean by error. Okay, so now let's take this concept a step further. We're saying that we are interested in how the sample is different from the population. So one thing that we can do to pursue that question is to also produce another type of distribution called a distribution of sample means. Right now, at this point, what you want to get is that we are now talking about a different kind of distribution. Here we had a population distribution. Here we had a sample distribution. Now we're going to talk about this thing called the distribution of sample means. Not a population distribution and not a sample distribution, but a sample means distribution, right? And that's the main difference here. Okay, so what is this distribution of sample means? First, I'll give you the written definition of what we're talking about here. I'm saying that distribution of sample means is a collection of sample means from all possible samples of an n obtained from a population. Okay, so this definition may not make a whole lot of sense. Therefore, I'm going to try to explain that definition by going back to talking about these distributions. So we just said, we've got some population distribution that we're interested in saying something about. We can't though, because we can't get to everyone. So before, we were pulling out individual participants and making a distribution of those individual participants' answers. Now, what we're going to do when we collect a distribution of sample means is we're still going to pull something out of the population. But this time, it's not going to be just an individual participant at a time that we're going to pull out. Instead, we're going to pull out a whole group of participants at a time, right? So there's going to be a group of participants that's going to come out here, a group that's going to come out here, and a group that's going to come out here. The way that we're going to denote each group or identify each group is as we pull those groups out, we're going to identify them by that group's sample mean. Okay, so I've gone into my population. I didn't just pull out one participant at a time. Here I've pulled out a whole group of participants at a time, and I've averaged what their answers were. Same thing here. Again, I reached in, pulled out a group of participants, and averaged their answers. Then same thing here. Now, one thing that you want to know about this is each group that comes out all have the same n. They all are the same sample size. But now what I'm going to do with these groups of participants is I'm going to create a distribution of those samples that I've just pulled out. Right, so maybe a way that you can see it here is now in this distribution, my distribution of sample means, I don't just have x values stacked on top of each other. Instead, what I'm going to have is sample means stacked on top of each other, right? Because now this is a collection of each group's mean that I got. And now that's what my histogram bars are made out of. Group sample means as opposed to individual participants. And we're still interested in figuring out what's the difference between the population and the sample. But the important thing that you're seeing here is that this is now what we're talking about when we use this term, distribution of sample means. Okay, so from here, I want to identify 3 characteristics of this new type of mean that we're talking about, or this new type of distribution that we're talking about, the distribution of sample means. First characteristic is, as you pull the participants out, the means, right, each group's entry is going to pile up around the mu, right? So you're dropping them in, they're piling in. As they come in, they're going to tend to pile up around the population mean, right? And so in this case, the population mean would line up right there. Okay, so that's the first characteristic. Everything's going to pile up around the mean line as they come in. Second characteristic is the curve, right? The curve that you end up creating with this new distribution is going to be normally distributed. And we should say that that's going to be the case as long as the population curve is normally distributed, but that usually is the case, that the population is normally distributed. Right, so what you should find is normal distribution here, and then the same normal distribution here. Just to remind you, what is normal distribution? Remember, normal distribution is where you have that bell curve shape with your data. Okay, so the third characteristic, the larger the n, the more that the mean is going to equal the population mean. Okay, so let me repeat that. The larger the n, right? So as you pull out your samples, if you can make your samples bigger, then it's going to be more likely that your sample mean is going to equal the population mean. Okay, so now from here, let's keep on talking about this new type of distribution that we're talking about, right? So remember, the whole new point of this chapter, so we've just talked about this now distribution of sample means. We're identifying it here, but it's also a big part of the chapter title as well. What is it? It is now this distribution that has these sample means in it instead of individual x values. Okay, so let's go to page 2 with this. Now we just need to talk about some characteristics, some further characteristics of these types of curves. One idea behind this is this thing called the central limit theorem. Basically, this is like a theory or like a statement that defines what we're talking about here. One way that definition works is we can say, if I take samples from a population, right? So exactly what we've been talking about. We've got some population that we're interested in. I'm pulling stuff out. I'm not just pulling out individual participants, but I'm pulling out samples. Okay, so if I do this, if I take samples from a population with a particular population mean and standard deviation, they will equal the sample mean and the sample standard deviation, right? So according to this theorem, what should happen is your sample information should equal your population information, right? If you think about it, you're pulling out all these samples from the population. That's a lot of participants, and it's because you're picking out a lot of participants. They should more closely align with what the population is telling you. Okay, so from there, we just want to focus in on some certain ways that this is going to happen. One way this is going to happen is with regard to shape, right? And by shape, we're talking about the shape of the curve. And remember that we're saying that shape is going to be smooth or normal. It's going to have that bell shape to it. So the thing that we want to say about this is that this is going to happen for any population that you are pulling samples out of, regardless of that population shape, mean, or standard deviation. Another thing that we can say about shape is that it's also going to happen rapidly. By rapidly, I'm saying that as you pull more and more samples out of the population, you're going to start to see that smooth curve shape appear relatively quickly. Should certainly happen by the time you get to an n of 30. Okay, so a couple of things that we wanted to say about shape there. Now I'm going to move on and talk about central tendency. Central tendency is basically this statement here. We're going back to talking about the sample mean minus the population mean. And we're just saying that this is called the expected value of the sample mean. Whatever this difference is what you should expect the sample mean to be. From there, though, so that's everything I want to say about this other term, central tendency. A big term that you really want to understand, that you want to get a solid grasp of, is coming back to this idea of variability. Right? So remember, we've talked about variability previously in this class, and we've basically said that it's a measure of how far each of your answers is from the mean, right? And it was basically the raw score minus the average that of the group that it came out of. We're still talking about variability in that way. Remember that what this led to was then a discussion of standard deviation, right? And I'm using the population standard deviation symbol here. What is that? You just want to remember standard deviation is when you have that curve and you've got that mean, trying to draw mu there. You've got that mean. Standard deviation was the standard distance away from the mean, right? And so standard deviation started out being 0 right under the mean, but as you move away from the mean, you're moving away in these standard units, right? And so that's one standard unit this way, one standard unit that way, right? So you want to hang on to that concept of what standard deviation is. Because now what we're going to talk about is when we create these distribution of sample means, we are now going to create a new type of standard deviation. Okay, so that's what I'm saying here. The standard deviation of the distribution of sample means is called the standard error of the sample mean. So we're still using the concept of standard deviation representing that standard distance from the mean, but now we're going to use it just a bit differently. How is it going to be a bit different? Now we're going to refer to standard deviation as the standard error of the sample mean. And it's also going to get a new symbol. Okay, so this symbol is this thing, the standard deviation of the distribution of sample means, or the standard error of x. Right, so you're seeing that it's still a standard deviation symbol. It's still that lowercase sigma, but now it's got this x bar subscript. And that's saying it is the standard deviation of a distribution that you create of sample means. So what's the formula for this new standard deviation then? Well, that new formula is this. In our problems that we're going to be doing, you're generally going to be given these two bits of information. The standard deviation of the population that you're pulling your samples out of. As you pull those samples out, how many participants are in each sample. You'll take that information and you'll calculate it in this division problem, and that will give you this standard error of x bar. Okay, what you're going to do with that is then you're going to use it in this z formula, right? What we're saying now, though, is there's going to be like this, let's say this new z formula that you're going to use it in, right? Because it's now a z formula that you're using with this distribution of sample means. How is that z formula going to look? It's going to take on this form. Now, let's think about what the z formula looked like before. Like, so the old z was this. It was z equals your raw score that you pulled out minus the mean of the group over that group's standard deviation, right? Notice how this is all like mostly sample information, right? We could even say a lowercase s representing sample standard deviation. Okay, so the way things are different now is they're saying you're no longer working with a raw score to begin with. Now it's always going to be some mean score that you've pulled out, and you're going to subtract the population mean from that, and you're going to use this standard error of x bar as your new standard deviation in this new z formula. Okay, so with that, I want to just go over a couple of practice problems that you can think about doing this with. This is basically the kind of problem that we're going to be seeing in the Chapter 7 odds and evens work. Let's see. So we're saying what we're going to be doing is, in these example problems, is we're going to calculate the z-score for a sample mean and find the probability associated with that sample mean. Basically, the exact same thing that we're talking about with this, right? So calculate the z-score for a sample mean. That's what we were doing here, except before it was calculating the z-score for a raw score. Once you have that z, then you went to the UNT and you looked at what was the proportion. Doing the same exact thing here. Let's just say that there is a bit of an added step, but let's go through a problem to see how this works. Let's see how I want to do this. Let's say that our problem is this to begin with. If I sample 16 students, what is the probability that the sample mean will be greater than 525? Right, so I'm pulling groups of students out. Here I'm saying that when I do this, I'm pulling out 16 students at a time. The question that is being asked here is, for that 16 students that I pull out, what's the probability that that group's mean is going to be greater than 525? Another way that that statement can be written is this way, right? Going back to what's the probability that something's going to happen. In this case, it's that I get a sample mean that's greater than 525. By the way, this is an example problem that's in the book, and it's on page 173 if you want to look it up. But in this problem, the authors of the book are generally going to give you some information that you can use. Let's look at what that is. First, remember one thing that we'd like to do that helps us understand the question is we'd like to draw a curve where we're basically getting a sense of what's being asked here. Right, so what's being asked is, what's the probability that I'm going to find some sample mean that's greater than 525? So that they're asking, what's the probability that I'm going to pull something out of that section of the curve, 525 and beyond? Okay. Okay. Other information that you'll be given to help you calculate this problem is you'll be told what the population mean is, right? So here they're saying it's 500, right? So that 500 would go right here. You're also being told what the standard deviation is, right? Now remember, this is the standard deviation of the population, right? Not the distribution of sample means. It's the standard deviation of that first group that you're working with, the population distribution. You're also given an n, right? And you were told that n here is 16 students at a time. And you're even told some specific sample mean amount, and that was that 525. Okay, so when you see this kind of problem in the book, first thing that you want to think is that there's an order of operations in which you're going to be doing things. And that's this order here. First, you're going to look to see if you can figure out from the problem what the standard error of x bar is, right? This new standard deviation. So let's put a first there. What you want to be thinking is, okay, I know that I want to get this. What's the formula for it? So you're going to try and find that standard deviation, and you're going to try and find that n, and you're going to put them in their proper spot. Once you have that, then that gives you the information you need to do the second thing, which is calculate this new z-score. But remember, the reason why you had to calculate that standard error first was because you needed it in the denominator of your new z equation. But again, we're being given all the information that we need. We've got that x bar, we've got our mu, and we've got that standard error. So once you have figured out what this z value is, you will then use that z value to go look it up at that unit normal table, right? You can look up the proportion. In this case, because we're talking about this section of the curve, for the z that we get, we're going to look up what is the tail in this example. And that tail will give us the proportion that's in that part of the curve. Okay, so let's go ahead and actually solve this problem. Solves, as you see here. First thing that we did was we calculated our standard error equation. It was 100 over the square root of 16, which equaled 100 over 4, which then equaled 25. Why did we calculate that? We calculated it so that then in our z equation, we now have our standard error that we need. Remember that the numerator part of the formula is your x bar minus your mu. So that's 525 minus that 500 over that standard error of 25. So that reduced to 25 over 25, or a z unit of 1. So now now that I know my z unit of 1, I go to my unit normal table, look up the tail section, and I see that I've got that 0.1587. And that is the answer that I'm looking for, right? So the answer is that there is this area under here that is 0.1587 of the proportion, or we can say there is a 15.87 chance that I will pull a sample mean greater than that 525. Okay, let's look at a second example problem for how to solve this. Maybe another more efficient way that the problem will be presented to you. Instead of the wording, you'll just get the symbols, right? But you want to read this exactly the same way that we've been reading it. They're asking, what is the probability that something's going to happen? In this case, what's the probability that I'm going to pick out some sample mean that is greater than 42? To begin with, we just want to make sure we understand what's being asked of us here. They're asking, what's the probability that you're going to get this sample mean value that's greater than the 42? So what's the probability that you're going to pull an x out of this section? Again, this looks like tail section to me. So we're going to go ahead and do our 3 steps of the equation of our answer to the problem. Let's go back here real quick. So that was our first, that was our second, and this is our third step. Okay, so first thing that we're doing, calculating that standard error. Oh, actually, let's look at all the information that we're being given. Right, so more likely than not, we're going to be given this information as well. We're going to be told what is the standard deviation of the population that the data is coming from. How many participants are we pulling out at a time? What is the population mean? And what is the sample mean that we're looking for? Okay, so given all this information, first thing I'm going to do is calculate that standard error of the x bar. Here I'm saying that it is 16 over the square root of 4. Why? Because that's our 16 and that's our 4. That reduces to 8, right? So now we know that we have a standard error of 8. We're going to use that 8 in our second thing that we're going to do. We calculate our new z. Here we're seeing that it's 42 minus 40, right? So that 42 minus the 40 over this 8, that gives us a z value of 0.25. So we're going to go to our unit normal table. We're going to look up the tail section again, right? Because that's the proportion that we're after. And we're finding that this time, the proportion of that we're interested in is 0.4013. Or we can say there is a 40.13% chance that we're going to pull something out of here. One thing that you might want to notice is that that seems like a pretty large percent for a tail. But think about exactly what it's saying. It's saying that if you have a curve and the z value at that curve is 0.25, that's when you're going to have this huge percent, right? You're going to have this huge tail, basically. I'm hoping that you're seeing why the tail is so big. It's basically so big because the z value in question is really close to the mean, right? Usually we're thinking in terms of being like 1 standard deviation unit out away from the mean. Here, we're a quarter of away from the mean of a standard deviation. And so that's why the percent is so big. Okay, so that's everything I've got for Chapter 7 textbook. I'll look forward to seeing you in the odds problems.